Everyone, I'm Yasmin Saadi, and here with me Renata Lardri. Thank you to each and every one of you for being here with us today. We are pleased to be able to welcome those of you that have been with us for a year, as well as those of you who are new. For our new audience, PyData, PyData has more than 140 chapters around the world, and PyData Jeddah is one of them. So PyData Jeddah is running by 7 heroes from Saudi Arabia. They are listed here. So let's move to the excited part. It's about our talk. I'm happy to introduce our speaker today, Dr. Thomas. He is the CEO and the founder of PyMC Labs, and he will talk about Bayesian modeling without the math and introduction to PyMC3. Please join me in welcoming Dr. Thomas. I know you are so excited to hear Dr. Thomas talking more than me, but I will try to keep it short. So I would like to thank our sponsor for their support, NumFocus and Muzon. Thank you for supporting our meetup. And if you want to know more about PyData, please visit PyData Global, pydata.org, the website. And to know more about our upcoming events, please follow us on Twitter. And one last thing, if you have any question, please write your question in the chat, and Renad will read the question to our speakers. So I think I will stop sharing now. Dr. Thomas, can you share your screen, or?
It still says host disabled participant screen sharing.
Okay, let me give you the permission.
All right.
Okay.
And can you see my screen?
Yes, we can.
Perfect. Well, thank you all so much for coming, and thanks for the organizer for having me. I'm really excited to present. I didn't know that there was a Jeddah or a PyData Jeddah to begin with, so I'm learning all kinds of new things. So hopefully you will too. By the end of this, we'll have learned something about Bayesian modeling. And really, this is out of my own accord of learning about Bayesian modeling and being really frustrated with this way of how it's often introduced. And it often doesn't. Yeah, so out of my own frustration of how Bayesian statistics is often taught, which is very math heavy. And I always thought that there needed to be a better way. So I've always been trying to explain Bayesian statistics in more intuitive ways. And this is basically my last iteration of how I think this can be introduced. So yeah, this is for everyone basically who does not have a solid math background, but still wants to know, okay, how can we think about this? And what I think is beautiful about Bayesian statistics is that we actually can do this. So there is an intuitive level of understanding that does not require a lot of math to understand. Okay, so let's dive into it. So I'm Thomas. I studied computational psychiatry. Before that, I went to study bioinformatics at the University of Tübingen. And now I run a company called PyMC Labs, which is a Bayesian consultancy. So, and we are the authors. So I'm one of the authors of PyMC3, and I'll talk about what that is. And yeah, so this is basically PyMC Labs. So all of us are core contributors to the library. And I'm really proud of the team that we have assembled. And it's basically just the most brilliant Bayesian modelers that I ever had the honor of working with. So just due to the nature of the project, we really have assembled all these people, and that's really amazing. So I'm really happy about that. And yeah, so it's a team of high hitters between we have mathematicians, neuroscientists, a Russian mathematician if you have. So that's Maxim. If you need mathematicians, they need to be Russian. That's the rule. Raveen built rockets at SpaceX. Now he's building Bayesian rockets at PyMC Labs. Yeah, so, and we solve really challenging industry problems wherever Bayesian modeling is important. Okay, so how do you think about Bayesian statistics? From high level, here's what I think that it allows you to do, and that is you can build models that are tailored to data. The analog I like to use is when I was growing up, there used to be Playmobil kids and Lego kids. And Playmobil is basically, I don't know how well this translates to an international audience. It's a German toy manufacturer. I think they're international. But anyway, you get the idea is you buy this, right? And it is the ambulance. And the only thing you can play with it is the ambulance. And here you have Lego, on the other hand, right, which is just a whole bunch of building blocks, and you can build the toy that was predestined to be built, but you can also just build your own toy, right? So you can reassemble these tools in their own way, and then, yeah, build whatever you want, right? So you can really build something that is targeted to your particular use case. And so this is basically how I think about Bayesian statistics is you just assemble the model that you want using building blocks, and the building blocks, as we will see, are probability distributions. Another really key point that is high level about Bayesian statistics and why you might want to use it is that it allows you to include any knowledge you already have about the problem. So, and this is in stark contrast to machine learning, right? So in machine learning, it's a very powerful tool, but it basically requires you to learn everything about the problem just from the data, right? You have a random forest classifier, and you have to have a huge data set for it to learn the patterns in there that are predictive. And if you really know much about your data set, well, then that's great, right? But a lot of times you do have a lot of knowledge about the structure of your problem, and that type of knowledge you might want to include in your model, right? So you have some type of expert knowledge, like maybe you have nested data, and hierarchical structure in your data set, or it's not a prediction problem, right? Maybe it's a decision-making problem, or just an inference problem where you don't want to predict something, but you just want to learn about your problem. Or really, it's one example I really like is COVID-19, right? How fast is it spreading? That is not a prediction problem, right? It's an inference problem, which is what's the reproduction rate at a given point in time. And there's all kinds of assumptions that we have and knowledge about how COVID-19 spreads that we can bake into this model and then get to that number that we want. So a huge class of problems is this inference problem. And I think it's in data science, we've been a little bit misled to think that machine learning is the only thing that really you should care about, because while it is powerful, it only applies to a very small set of problems. And Bayesian statistics, on the other hand, is applies to a much broader set because, well, you can do machine learning, but you can do so much more. For example, A/B testing, right? This is something where, I mean, this is not a prediction problem, right? So you have two versions of the website. You have your control, you have the current version, and then you have another version of your website where maybe you change the color of the sign up button, right? And you want to know which one of those leads to more signups or sales or whatever the metric is that you care about. And so you can basically structure this problem. And well, as I said, it's not a prediction problem, right? We want to know which of those two is better, or what is the conversion rate between those two websites. So you can say this is a hypothesis testing problem or a decision-making problem, or just generally an inference problem. So let's get very concrete here and look at data that we have collected, right? So we test both of these versions on our website, and most of the people don't convert, right? They don't sign up to our website, but if it's one, then they do convert. And we do this for both. This is 100 trials. So 100 users visit version A of the website, 100 users visit version B of the website. And now we want to know, well, which one is better? Well, how do we decide that? Well, one very simple thing is, well, we can just take the mean of that, right? NumPy.mean, A conversion 0.07, so 7% of people convert. And for B, it's 17% that convert. So apparently, version B is better, right? Well, who knows, right? one critical piece of information is missing from this number, right? And that is, how sure am I in this number? So for example, I could get 0.07 if it was just 10 conversions, right? Or if it's a million conversions, if it's a million data points, right? So the length of this vector, right? The more data I have, well, the more sure am I that it's actually and that it's actually 7%, right? If it's just very few, well, I will be very uncertain. But with a lot of data, I will be much more certain. So this is basically what is missing if you're doing this. So this is called a point estimate, right? Because it's just a single number. And really what we want is to encode the information in making that decision, right? How certain are we that this version is actually better than this? Because there is noise in here, right? Okay, so let's assume we have a magic machine. And that magic machine provides plausible values of conversion rates. So rather than just saying, okay, there's a single number here, 7% is the only number that explains the conversion rate of this data set. Now we're saying, well, it could also be 0.075, right? That also explains this data set pretty well. Could it also be 0.9? No, probably not, right? That is very unlikely. That's implausible. The number of conversions in this being 90% with this data set is impossible. But 0.5 might be possible, or 0.08 might be possible, right? So these are all possible, plausible values that explain this data. And this is what that magic machine produces. So in this magic machine, which we'll, of course, talk more about, but let's just assume we have it, and we feed it data, and it gives me plausible values of conversion rates. So it says, okay, 11% could explain this data well, or 8% could explain this data well, or 5% could explain this data well. And well, what I can do then is, so for the conversion rate of website A, I just draw a histogram, right? Over all plausible values. And this basically tells me that, okay, well, 0.07, which is the point estimate that I've gotten before, that is the most likely value, right? But it could also be 15%. That's not many plausible values in that range, right? But still, I don't want to rule this out. But it's definitely not going to be larger than 20%. That is just incompatible with the data that I observed. Okay, cool. So if I had this, right, I think it's pretty obvious that this would be useful. To drive this point home further, there's now a lot of interesting things that we can do with this. So for example, we might want to know how many plausible values are there above 10%, right? So maybe 10% is for us an important cutoff where we want to know, okay, if it's below 10%, then it's bad. If it's above 10%, then it's good. And how do we answer that question? Well, we just count, right? We just take the number of samples that are smaller than 0.1 and the number of samples that are larger than 0.1, and we just divide by the sum, right? So 82% of samples are below 0.1 and 18 are above. And already now we are doing statistics. And the statistical statement behind this is that the probability that the conversion rate of A is larger than 10% is 18%, right? So now all of a sudden, just by having plausible values, and we don't yet know how we get those plausible values, right? But if we have, well, then we can just answer all these interesting questions. And with the point estimate, we weren't able to do that. Now, I can compute these plausible values for conversion rates for website A and for conversion rates for website B. And that gives me two histograms, right? So, and here already, just by looking at it, we can see, okay, it does seem like there is that the plausible conversion rates for B are definitely much higher than those for A. So that's cool. And here we have the conversion rate so now we might want to ask the question that we actually care about, which is that we have what is the probability that the conversion rate of website A is better than that of version B, right? So that the old version is better than the new one. And what's cool is that, well, with our plausible values, we can just do that, right? We can just say, okay, the conversion rate, how many samples from my distribution of over here are larger than the values over here. And then I just count those up too. That is 1.8%. So that's nothing, right? And again, now we have a statistical statement embedded here. We know that the probability that the conversion rate of A is larger than that of B is 1.8%. So that's kind of cool, right? So just by having these plausible values, I can just slice and dice this histogram in all kinds of ways and answer all these statistical probability questions. So obviously now that begs the question, how can we build this machine, right? And well, that's where a very smart person came in called Thomas Bayes, very proud to share his first name at least, who was like, okay, well, we can just use Bayesian statistics. Well, that's not what he said, but that's what everyone else said. So he figured out a very simple reformulation of Bayes' formula up here, but that's actually not even that important, right? The key is that this allows us to build this box. So you're probably wondering what's in the box. So again, trying to find a high-level overview of how we could think about this. Let's say that we have a solution generator, right? And that generates values for my parameters. And these are conversion rates. And I don't really know ahead of time that these conversion rates, whether they're plausible or not. So this just generates, basically it's a random number generator. It's a little bit smarter than that, but that's at the core what it does. And as you can see, the values that it generates, this random number generator, are not even plausible. So for example, negative numbers. So obviously the conversion rate can be negative, right? The minimum it has is 0%, but the random number generator doesn't really care about that. So this just generates solutions. And then we have our data, and then we have a solution evaluator. And that is basically the one that says, okay, a value of 0.054 is plausible. So we're going to store that into our bucket of plausible solutions. And then we have, for example, minus 0.013. That is implausible, so we throw that away. So yeah, so this is basically how this works in a specific setting. Of course, I haven't really told you, well, how this works or what the solution evaluator is. That's what we're going to look at next. But from a high level, this is how you can think about this. Now, for those of you who are familiar with Bayesian statistics, you might notice that I'm using different terms here. And I'm doing this just because I don't really like the original terms. They are just a bit archaic, right? So for example, this random number generator is really called Markov chain Monte Carlo sampler. But I mean, what the hell does that even mean? Or these here, the plausible solutions to my problem are posterior samples. And here, the evaluator, that is my Bayesian model. But just so you know that how these terms map to what other people call them instead of just me. Okay, so let's dive into this. So clearly the most important part is the solution evaluator. How can I say whether a conversion rate that someone suggests to me is plausible or not? Does it explain the data well or not? That's really what we're asking here. And for that, we need two things. The first one is, well, we need a way to evaluate the solution. And well, we can just think about this for a second. So out of 100 visits, we get 7 conversions for version A. So which conversion probability plausibly explains this data? So what we want is something where we can input a conversion probability, right? So for example, 90%. And then I want to know how well does the conversion rate 90% explain the data? And that is what is plotted here on the y-axis. So I have this function, I input a conversion rate, and it tells me whether that is plausible or not. And based on that, I can decide whether I want to keep that proposed conversion rate or not. And the function that does this is called the likelihood function. As inputs, it takes the number of trials, 100, and the number of successes 7, and the conversion probability we want to evaluate. So all 3 go into this function, and then it returns how well this conversion probability explains the data. And the particular shape of this function is called a binomial distribution. So if you have count data of successes and failures, then it's the binomial distribution. So there are all kinds of different probability distributions for all kinds of different data sets. So if you have successes, then it's binomial. If you have just coin flips, right, then it's Bernoulli, or yeah, kind of a normal distribution if it's just continuous and a mean. And there's a whole bunch of them. If you have arrival times, then it's a Poisson distribution. So there's all these different likelihood functions that we're often using. And you do have to know something about statistics in order to decide which is which, but often the choice is rather clear. So the next thing we can think about is how we're updating the space of plausible solutions. Because yeah, so this is one thing I haven't told you about, and that is that we have not just the posterior space of plausible solutions, but we also have a prior space of plausible solutions. And the way this works is that you can imagine that we have, before we have seen any data, right? And this is coming back to what I said at the very beginning, where we have expert knowledge of a problem. And part of that expert knowledge might be that we know that, for example, no website in this world has a conversion rate of 100%, right? That just doesn't exist. Most likely the conversion rate will be lower than 50%, right? We just know this. We don't have to gather any data to know this. So it's going to be low, but how low, I don't know. And we can define this in the model and say, okay, without having seen any data, what do I think are plausible solutions to this problem? And this is what is plotted here, also as a histogram of values. So all of these values here do I deem plausible without having seen the data. So this is just me based on, well, not really knowing a lot about websites and A/B tests, but this is just what I personally imagine. Now, some people here might actually know much more about A/B tests, and they will say, well, actually, this distribution is all wrong. Here's a better one, and then we can use that. So that would be great. So we start with this prior belief, and then what we do is we observe data, right? This is the binary events that I've observed, and then we evaluate the solutions. This is what we do with the Bayesian model. And then we get to that posterior space of plausible solutions. So this is already what we looked at before, right? So we have this, all the values that plausibly explain the data. And the new thing that I told you about now is that we also have the plausible values without having seen any data. And really, this is a very natural way for me to think about Bayesian statistics, is that we're just updating our beliefs. So we have beliefs of plausible values about the world. And this is how humans just go about in the world, right? We have some hypothesis of how the world works. Well, we have many hypotheses of how the world works, right? And then we observe like, oh, well, this hypothesis I had of how the world works clearly was not correct, right? Because you now gather data, you gain experience in life and see, oh, that's not how the world works. And then you discard that idea. And over time, you just refine your hypotheses to those that actually stand the test of time. Well, hopefully that's what you're doing, but that's not what everyone is doing. But if you are scientifically inclined, you see whatever works for you in your life and stick with those hypotheses that seem to explain what you're seeing. So this is how Bayesian updating works and how you can think of learning from data by shifting beliefs around. So far, this has all just been very, very high level and conceptual, but now let's actually see how we are doing this. So we got a PyData meetup, so I'm going to show some Python code. Here I'm using PyMC3, which is a probabilistic program written in Python that allows you to build these types of models, these magic boxes, in Python. Really what's special about it is that you don't have to have an external language that you're using. You can just use Python for building your models. And the first thing we do is we import PyMC3 as PM. So this is what we're going to call it. And then the first line, and this is boilerplate, every line will have this, we're setting up a context manager, this with keyword. So we're instantiating a model, and we're tying it to this model variable. And that actually doesn't really matter all that much. This is boilerplate code. Every model will have this line. What gets interesting is what happens beneath that, because what this says is that everything that happens underneath here is going to be tied to this model. So this just says, okay, let me define a model that I call model A, and that model has parameters. And the parameter in this case for modeling the conversion rates of version A is just the conversion rate parameter, right? This is what I want to infer. What is the conversion rate? And as I said before, I'm assigning priors, which are my beliefs of plausible values of conversion rates before I've seen any data. And this is this distribution, which is described by so-called beta distribution. So these are, again, these probability distributions. And beta distributions always occur when you have percentages. So this is from 0 to 100%. So that's why this is a beta distribution. And this comes from PyMC3. So we're just going to say, okay, without having seen any data, I'm going to believe this is beta distributed. The first argument is a name. The second argument are the parameters to that distribution. So these probability distributions are parameterized by certain values, and they don't often make that much sense. So here I just chose two values that give it this shape. So this is often how you do it. You just know the shape that you want, and you give it the parameters to give it that shape. So it's not really important how I came up with it. I just played around with it to get something that looked like this, right? If I plug in different values, I get different shapes, like maybe if I do alpha 10 and beta 2, so I just flip them around, and this will just look mirrored around 50%. So this will be high probabilities. Okay, so that sets up my parameter that I want to infer and assigns a prior to that. Next thing I need to worry about is the likelihood function. And again, this is what we talked about. And we decided that this was a binomial distribution, which is this function that gives me, for every conversion probability, it tells me how likely that is. And here I now, again, give it a name. I specify n 100, so we have 100 different trials that we had, and 7 of those converted. So that is what I have observed, right? And this is the keyword argument that makes this into a likelihood function. So this says, okay, this is not a parameter to infer. This is actually something that I have observed. I've observed that 7 out of 100 have converted. And now I have to say, okay, well, what is the probability of a conversion occurring, right? So 7 out of 100, but is that actually a conversion probability of 7%? Or could it also be 8%, right? Well, it's not clear. That is what I want to infer. And that's where I pass in this other parameter that I've defined. So this is what ties it together. I have this likelihood function that describes my data. I have this parameter that I want to infer, and that parameter itself has a prior distribution. So hopefully that makes sense. And now what I need to do is, so this specifies the model, but there's one thing now. I have to basically run this proposal generator for different solutions, right? So if you remember here, we have the solution generator. We still need to run this and get a plausible solution. So far we have now only built the solution evaluator. Now we need to do this, but the good thing is that this is easy because this is completely automatic. And in PyMC3, what you have to do is call pm.sample. So this basically runs that loop where it asks the model, okay, is minus 0.05 a plausible value? And the model says, no, that's impossible. So then we're going to throw that away. Is 0.07 a plausible value? Yes, that's a great value because that's exactly how many conversions we observed. So we're going to keep that in our plausible value store. And so this is basically that posterior, that collection of variables that we care about. And what's cool is now that we have this, right? So this is all we had to do. So this gets us to these values of plausible values for the conversion rate. And yeah, so that is cool. And now all we need to do is actually just inquire that posterior distribution. So for example, the things that I showed you in the beginning, we can just say, okay, what type of values from the conversion rate A are smaller than 0.1? And that gives me a Boolean array. Then if I call the mean on that, then that tells me 82. So 82% probability that the conversion rate is smaller than 10%. And if you remember from the very beginning, that's exactly the thing that I showed you here, right? So this is how I got the number. So I ran the sampler, I get this full distribution, and then I just say, okay, what percentage of those samples is smaller than 0.1? And that's that number. So this is just to show you how we can then very easily work with that and do statistics. And this makes just way more sense to me, at least, than, for example, frequentist statistics, where this would be much more cumbersome to do. Or that question that I had before of, is the conversion rate A higher than conversion rate B? So I just compare, run the model for A and run the model for B. I haven't showed you the one for B, but it's the same. And then again, that gives me a Boolean array. If I call the mean, I get the probability. Pretty simple stuff, I hope. So this basically just concludes this section of the talk. There is, of course, I've just been scratching the surface here. There's so much more you do. And really, this is the main point that I want you to take home is, so you have this tool and allows you to build models, all kinds of models tailored to your data. And you don't just get a single answer, but you get all answers that are plausible. And this allows you to specify the uncertainty and allows you to answer questions in a statistical way. But there's so much more you can do. You can do linear regressions, right? So this is a model that where now we have a normal likelihood, right? Because we assume that the error here, these data points are normally distributed, a normal error. And here we have the true regression line in yellow. And again, we don't just get a single answer, we don't just get a single regression line as our answer, but we get all regression lines that explain this data well. So as you can see, we can't decide between them. They all do a good job of explaining this. And this is just a couple of lines in PyMC3. Or maybe you have outliers, right? So now I have these 3 points in here that are skewing this result up, right? So the normal likelihood function is very susceptible to outliers because it has very small tails. So small, like large deviations away from the mean will affect this strongly and bias this. But now, because I have the flexibility of Bayesian statistics, I can just say, okay, well, there are outliers in here, that the normal distribution is not a good fit. Instead, I can use a different likelihood function to explain this, which in this case is the student t distribution. And that allows for values far away from the mean, this orange line. And if I run the regression that way, I just need to say now change a single line of code in the model, all of a sudden I have a robust regression model that is not susceptible to these outliers. So I'm aware that I'm going fast. So this is just a high level to give you an idea. You don't need to understand everything here. Another really powerful concept is hierarchical models. So often you have nested data. For example, maybe we don't just have a single website for which we run an A/B test, but we have 100 websites. Maybe you are the person who is, you're the A/B testing company, right? And you have all these different websites that you're testing all the time. And you want to know which of those is better. Well, you can actually learn what you, so you can just run separate models for each of those websites, right? But most likely they will share some similarity in these websites. And you can exploit that in a hierarchical model by embedding this. So you can say, okay, well, I know that all of these individual websites, conversion rates, actually share similarity, and I'm explaining this with a shared parameter between all these different websites. So we are tying them together, and that allows us to model the similarities and differences simultaneously. So these hierarchical models are very powerful. You can also do very classical hypothesis testing. Say we have a drug and a placebo. We want to know which of those is better. That's basically the A/B testing one. There is something called Bayesian estimation supersedes the t-test, or BEST. That's a standardized hypothesis test similar to this, to the t-test that you know from frequentist statistics. But this one is better. We can have mixture models where maybe this is not just a single distribution, but it's made up out of 3 individual distributions. And we can infer those distributions underneath and model this data. If you have data that is not just a single regression, but maybe this is a time series and this could change over time, right? So maybe this is, there's a very powerful example of CO2 concentration in the atmosphere, which is changing over time. And so there's this very flexible class of models called Gaussian processes that you can fit to all these time series and get something that explains it given the data. So this is very powerful, and you can also then predict into the future. And note that these predictions also have a lot of have uncertainty around that. So you don't just get the most likely future path, which would be this red line, but you also get all kinds of other ones that reasonably well could explain the future. So that concept of uncertainty is very important. You can do survival analysis. And of course, you can also do deep learning. So a lot of the field of deep learning now has embraced Bayesian statistics of starting to embed these models, or rather to allow you can express Bayesian, you can express deep nets in Bayesian form in terms, and then get a lot of interesting benefits from that. So if that is interesting, definitely check us out at PyMCLabs.io. You can visit my blog, where I write about this stuff. So a lot of the examples that I just showed in the last section are from my blog. Here's the website for PyMC, and here's a great book on learning this in a more proper way. So yeah, with that, I'd like to thank you for your attention, and would be happy to take any questions that might have come up.
Thank you so much, Dr. Thomas, for this valuable information. We really do appreciate it. We have some questions I would like to tell it to you, please. Our first question: what are some common pitfalls that practitioners fall into when building Bayesian models on PyMC3?
What are common pitfalls when building these models?
Yes.
Well, there's a whole bunch of them. So the biggest one is that you misspecify the model. So you write down a model, but you didn't choose the right prior, or like, for example, let's say here, right? So you choose a prior that actually is not, that is far away from the actual solution space, and then the sample will have a hard time. So the most difficult thing is building the right model for your data. And this is an iterative process, and it takes time, because you can't just say, okay, here's a bunch of data and I'll predict. You have to really understand your data and learn about your data. And but that is also the superpower of this, right? Is that you can, by being forced to write out your assumptions in this model and then test them on data, you really are learning something about your problem. But yeah, so this is, I would say, one of the biggest stumbling blocks is when things go wrong, right? So the sampler here, for example, it's very powerful and works most of the time. But if your model is not specified well, then it will fail. And then that looks very ugly, but it's really just trying to tell you that there is something wrong with your model. So yeah, that I would say is the most common thing that we see.
Thank you. Our second question is that random sampler is actually randomly generating values for parameters of possible posterior distributions, right?
Very close, yes. So basically it's generating individual values, and then it's testing those values, whether they make sense. And then if they make sense, then I put them into my collection of posterior samples, yes. So, but it's not generating posterior distributions, but it is the thing that makes up the posterior distribution. So a lot of the collection of all MC samples is my approximation of the posterior distribution. So yeah, that's the only correction.
Yes, it's clear. Okay, our third question is it possible to choose a prior distribution without an initial set of data to base or assumption to base our assumption on?
Yes. So usually then you would call that an uninformed prior. And so for example, here I could have also said, that without having seen the data, right, I do have some information here, and that is that the conversion rate must be between 0 and 100%. So that is something that I know, right? So that is part of the prior. But now I could say, okay, well, in between that range, I'm going to assume that all values are equally plausible. So then that would just be uniform distribution from 0 to 100%. And then I would say, okay, I'm not biasing the inference at all. And that is what is called an uninformed prior. You can do that, but that is often ill-advised because very rarely, right, do you really think that all values are equally likely. You always have some information. But yeah, so I would say the more information you have and the more you can constrain a prior, the better. But yeah, if you don't know, well, then you just set very wide priors. But yeah, there is this sentiment, right, that is often underlying that type of question where it's like, oh, I don't want to bias my inference. I want the data to speak for itself. And that sounds so seductive, right, that it must be true, but actually it's completely stupid. The data can't speak for itself. And the data is completely schizophrenic. The data is super noisy and is a mess, right? So thinking that could speak anything that would be reasonable is, yeah, I don't think makes a lot of sense. We really need to have, we can only really ever make inference when we make assumptions, right? And so, yeah, that there is something that could be uninformed or non-biased is impossible. It's always going to be biased in some way. So, but here we're being very explicit about our biases that we're doing, and these biases are good. You do want to bias your inference to be in a range of values that you know is going to be plausible. You don't want answers that just don't make any sense.
Yes, thank you. It's clear. Okay, our first question was, how many parameters can PyMC3 estimate? Some of our attendees are very curious to know the scalability PyMC can do.
Mm-hmm. Yeah, so it used to be the case that you could build like models with 10 parameters or maybe 50 parameters, but now these samplers are so extremely powerful, and the tools also are just so fast that. So we've built models with over 50, 60,000 parameters. Say probably in the hundreds of thousands is where probably the light speed limit probably could push reasonably well estimated. I would say up to 100,000 is definitely like possible, and then that would take a couple of hours. But I would stress that. So we have built this model, right, with, for example, 40,000 parameters, and that fits super well, and it was, again, took like 2 hours. But that was still a lot of work to get to where it sampled that quickly. So you need, the model needs to be well specified, right? So these samplers are extremely powerful, but they're not magic. And if you have like really weird shaped posterior, right, a difficult posterior distribution to sample from, then that is why it's going to be slow. So usually it's slow not because of the number of parameters, but because of the data. But usually it's slow because your posterior is really difficult. And in that case, you need to go in and fix your model so that the posterior distribution looks better. And that is difficult to do. And that is often what we do with our consultancy, is people come with us with models that are running, but they're very slow. And we don't do anything, but we just rewrite their model in a way where it's actually then faster to sample. So yeah, that's mostly the constraint, is how the model is specified. But yeah, so you can fit very, very complicated models.
Interesting. Just know that. Okay. Our first question. In the first example, would bootstrapping would work for estimating the uncertainty around 0.07 conversion rates, like randomly sampling from the data 1,000 times?
Mm-hmm. Yep. So Bootstrap is definitely the right way to think about this, right? So with Bootstrap, I could also derive these samples, and that's fine. So if the alternative to Bootstrap is point estimate, then definitely do Bootstrap. That's great. The Bootstrap, however, has a whole bunch of drawbacks, which I'm not going to go into. But well, one of them, for example, is that all you're doing is resampling data, right? There's not a real model of how you think the world works behind this. So it's very constrained in this. So in this particular example, for example, I could have done this and probably got something different. It got something similar. But now let's assume, again, that we have maybe this hierarchical structure of the data set where I don't just have one website with an A/B test, but 100 websites with an A/B test, and I want to share knowledge between them. Well, a Bootstrap does not allow you to do that. So yeah, this is where this flexibility comes in, and the power of building more complicated models. And the other one is also just a theoretical consideration. So here, the uncertainty that we're getting is very much stands on very solid theoretical foundation, while the Bootstrap does not come with such strong guarantees of this. So, but yeah, think about this like the uncertainty you get from Bootstrap, but it's better than Bootstrap.
Cool. Okay. How to tell if outliers are the result of noise or from a fat-tailed distribution?
Yeah, and this is a cool question. So in this model that I showed here, you can't really do that. What you can do is build another model. And there's an example of this on our website. You build a mixture model and you say, okay, there's two different distributions. There's one distribution that is the samples that are coming from this linear regression. And then there's another distribution, which is my outlier distribution. And I'm gonna, for every point, assume that it comes from one of these two distributions, either from the outlier distribution or from the linear regression distribution. And that model, it's called a Hogg model, H-O-G-G, can then allow you to say, okay, these are outliers, they're coming from this outlier distribution, which is my mixer model estimated, and these are inliers, and they're well explained by this distribution. And because these samples then are not going to go into this likelihood function here, even if I use a normal distribution for my likelihood function, it's still going to give me the right estimate. So this won't be biased because these samples up here are explained by another distribution. So yeah, this model can't, but another model, which is a mixture model, can.
Oh, interesting. Okay, can you share some use cases of Bayesian analysis that you have come across in your consultancy? Is it always better to adopt a Bayesian approach than a frequentist approach?
Mm-hmm. So yeah, we have clients in all kinds of different industries. So one, for example, is with a company called Everrisk, who are building risk models. So they're, and this might be relevant for Saudi Arabia, right? So very wealthy individuals, they have a lot of their money in the stock market, but they also have it in private equity. So venture capital funds, for example. And there, what we did for them was, so because they're private, right, they're not traded on the stock market, and it's very difficult to infer returns of that, or the price of a VC fund. And the model that we built allowed you to estimate the returns of private equity investments, given capital calls and distributions. So yeah, just by how much goes into a fund and how much comes out of a fund, we were able to infer the returns, which is a latent distribution. So there's one example in financial modeling. But also, we're working with an agricultural company, and they are planting all these crops on these fields, and in different fields, they're testing different crops, and then want to know which crops are best. But then there's all this variation, right? Sometimes on the right side of the field, there's more sun than the other side, or there's different waters. So I want to estimate this underlying distribution and then know which crops are the most powerful. So it's used for that. For example, there's one of our clients. Another client is the pharma company Roche. So they are testing humans to see how well a certain drug impacts their working memory. So how many items can they store in their working memory under this drug or off the drug. And for that, we also built a Bayesian model to infer, okay, how many items can someone keep in their mind at the same time. So as you can see, it's very wide in these modeling problems. And I would go as far as saying yes, Bayesian statistics is always better than frequentist. And the reason is that frequentist really doesn't make sense. I'm not saying that it's wrong because the mathematical theory is correct, but it's not the thing that you usually care about. And unfortunately, I can't really go into this just because frequentist statistics really does make so little sense that if I start to explain what it's actually trying to compute, that it would lose everyone on this call, where they would just say, well, that just doesn't make any sense. And that's the point. So my summary is frequentist statistics gives you answers to questions that don't make any sense, while Bayesian statistics gives you answers to questions that do make sense. Both of them are correct, but in one case, the questions don't make sense. And just one last point on this. If you ask scientists what a p-value is, a frequentist p-value is, they explain to you what a Bayesian p-value is. No one really understands what this really is. And that's highly problematic because, yeah, at the end of the day, it's not really what you want.
Yes, clear. Our last but not least question, how explainable are Bayesian models? Does SHAP values, SHAP stands for Shapley Additive Explanations, apply to Bayesian models as well?
So yeah, that's super great to have that as the last question. So yeah, these models are very explainable, which is cool. So because we have a model of how the world works and latent parameters that are infer, I can really inquire the model and say, okay, well, this is the driver of this pattern of data. So yeah, you can really communicate these models to other people in the company, or you can just ask people in the company, okay, how's your problem structured, right? And then you build a model that is mapping that problem most accurately. And then, yeah, you can really inquire the model and learn about your data set. And this is in stark contrast to machine learning, where you can't really ask the model what it has learned. So it's very explainable. I don't know what SHAP values are, so I can't answer that in a part of this. But yeah, so yeah, I really enjoyed these questions. This is amazing. I'm glad that people really seem to have gotten it.
Okay, we have one extra question came up. Do you think that Bayesian deep learning is the answer for explainability to the deep learning models?
No, I don't think so. So usually these models are explainable if you build them in a way that they are explainable. But if you can certainly build models that are very hard to understand. And if you, for example, if you build a neural network model as a Bayesian model, then that is not going to inherently be explainable because still the model is just learning arbitrary things. So you're doing machine learning, black box, and you can't understand in Bayesian modeling, and then you also still can't explain, then you can't still not, you still can't explain it in the Bayesian framework. So that by itself does not make it explainable. But usually the type of models that you're building are a much closer map to the problem that you're having. And in that case, where you build a model that is grounded in understanding of your problem, right? Then the model is understandable. If you just build a model that just infers some crazy hyperplane in some abstract space, like a deep net, then it's still not going to be explainable.
Interesting. Okay, there's no more questions. Yasmin, the mic is yours.
Thank you so much, Dr. Thomas, for your time. And thank you. It was a great talk. And thank you all for joining. Follow us on Twitter to know our upcoming events. And yeah, this is the end of our meetup.
Thanks, everyone. Bye.
Thanks. Bye. Bye.